Good morning students. Today we are going to discuss about specific heats of monoatomic gases. So let me start. Specific heats of monoatomic, diatomic, triatomic and polyatomic gases. So this is our topic. So here one question is given to us. We have to find question number 26 by using law of equipartition of energy determine the values of Cp, Cv and gamma. So what is Cp here? Cp is specific heat at constant pressure, correct? And what is Cv? Cv is specific heat at constant volume. So first we will find here Cv. For formula to find the value of Cv is du upon dt. So first let me tell you from where we are getting this formula. So by first law of thermodynamics, we can write dq is equal to du plus dw, and this equation can be written as dq is equal to du plus p delta v, correct? So here we have to find the value of du upon dt. So remember that we are going to find the value of Cv, and Cv is what it is: specific heat at constant value of volume. So we know that in this equation, if the value of volume is constant, the work done will be 0 and du is equal to dq, correct? So in this way we can write that Cv, which is equal to dq upon dt, it can be written as du upon dt. So let me write this is capital T here, just a second. This is capital T, because here we are going to differentiate it with respect to temperature, not with respect to time. So this is the formula: Cv is equal to du upon dt, correct? Now we have to find first the value of Cv for monoatomic gas. So this is our first topic, Cv for monoatomic gas. First we should find the value of degree of freedom for a monoatomic gas. Degree of freedom for monoatomic gas may be 1, maybe 2, maybe 3. It depends on the molecule of gas. The molecule of gas is making motion in making motion in a line, comma, a plane, comma, a space. If the molecule is moving in a line, so the degree of freedom will be 1, and if the molecule is moving in plane, the degree of freedom will be 2, and if the molecule is moving in space, the degree of freedom is 3. So here we are taking which one? The third case, and the third case is where the gas molecule is moving in a space, correct? So in this way, just a second. Now the next thing is we are going to find the value of degree of freedom for a monoatomic gas, and we are taking it 3. Okay, so now we have to find the value of U. What is U here? U is total internal energy of 1 mole of a monoatomic gas. So U can be written as 1/2 kBT is the amount of energy which is carried by each degree of freedom. It will be multiplied by 3 because total number of degree of freedom of a monoatomic gas molecule when it is moving in space are 3, and multiplied by Na. What is Na here? It is Avogadro number because we are going to find the value of U for 1 mole, and in 1 mole the number of molecules are Na. So this is the value of U. U can be written as 3/2 kBT multiplied by Na. We know that R, which is universal gas constant, divided by Na is equal to Boltzmann constant. So if we are multiplying these two, Na multiplied by Kb, it will gives us R. So we can write the value of total internal energy 3/2 RT, correct? So from here we can find the value of Cv. We know that the formula for Cv is du upon dt. So we can write it like this: first order derivative of U with respect to t, and the value of U is 3/2 RT for a monoatomic gas whose molecule is moving in a space. So here we can see that 3/2 R is constant, so it can be taken outside the differentiation, and the remaining part is d by dt of t. So the value of this can be written as 1 with the help of this formula, d by dx of x raised to the power n, nx raised to the power n minus 1. So if we are just writing it like this, x raised to the power 1, it can be written as 1 into x into 1 minus 1. So 1 multiplied by x raised to the power 0, 1 multiplied by 1, and the final answer is 1. So in this way we can find the value of Cv. It comes out 3/2 R, and we know that by Mayer's formula, Cp minus Cv is equal to R. So that implies Cp is equal to Cv plus R. We already calculated the value of Cv. So Cv is 3/2 R, plus R can be written as 2R by 2. So that's why the value of Cp comes out 5R divided by 2. So these are the two values of Cv and Cp. From here, if we want to find the value of specific heat ratio, one more important thing which can be written as gamma. Just a second, let me check the color. So the value of gamma we are going to find now. So gamma can be written as Cp upon Cv. And what is gamma? This is specific heat ratio, correct? And we already calculated the value Cp, which is 5R divided by 2 divided by Cv is 3R divided by 2. It can be solved like this: Fr divided by 2 multiplied by 2 divided by 3R. So 2 cancel, RR cancel. So that's come gamma is equal to 5 by 3. So these are the values for monoatomic gas. You can understand this. We are taking degree of freedom 3. So here we are finding the total internal energy, correct? Total internal energy of 1 mole of a monoatomic gas when we are taking its degree of freedom 3, correct? So in this way we are finding the value of 4 things. One is V, one is Cv, one is Cp, and one is gamma. The value of gamma comes out 5 upon 3, correct? Similarly, we can find the next thing, which is just a second. Now the next part of the topic is specific heat of a diatomic gas. So let me start. Next part is specific heats of diatomic gas, correct? So again we have to find the value of U. What is U? The total internal energy of a diatomic gas of 1 mole. The amount of substance is here diatomic gas, and the amount of substance is, that is important, amount of substance is equal to 1 mole of diatomic gas, correct? 1 mole of diatomic gas is our subject. For that we are going to find the value of internal energy. So we are taking the help of law of equipartition of energy, which says that each degree of freedom will carry this much amount of energy, which is 1 by 2 kBT multiplied by degree of freedom. Now in diatomic case, diatomic gas will have 5 degree of freedom at normal temperature, which can be written as normal room temperature. The second condition is diatomic gas will have 7 degree of freedom if temperature is approximately equal to 5000 Kelvin. Here we have to keep this thing in our mind, that 2 degree of freedom will be additional because of vibrational motion. So here we are dealing simple case, which is at normal temperature. So the number of degree of freedom can be taken 5 multiplied by Na. Na is what? Total number of molecules in 1 mole of substance. So this left side U will be internal energy. I can write it here. Internal energy of 1 mole, correct? So U can be written as 5 by 2 Kb multiplied by Na multiplied by T, and this U can be written as 5 by 2 RT. Now the next thing is Cv. Cv is what? Specific heat at constant volume. It can be written as du upon dt, first order derivative of internal energy with respect to temperature. So d by dt of u is how much? 5 by 2 RT, and I can write it like this: 5 by 2 R is constant, so it can be taken outside the differentiation. The remaining part can be written as d by dt of T, and the final answer comes out 5 by 2 R. So this is the value of CV. CV is how much? 5 by 2 R. Now we will take the help of Mayer's formula. By Mayer's formula, we can write this: Cp minus Cv is equal to R. So we can write Cp is equal to Cv plus R, and the value of Cv is 5 by 2R, and R can be written as 2R by 2. So that's why the value of Cb comes out 7R by 2. And now if we want to find the value of gamma, which is specific heat ratio, so gamma can be written as Cp upon Cv. So here the value of Cp, sorry, I wrote here Cv, just a second, it must be Cp, okay. So the value is Cp upon Cv. So Cp value is 7R by 2, and the value of Cv is 5R by 2. So it can be written as 7R by 2 multiplied by 2 by 5R. R cancel, 2 cancel. That implies gamma comes out 7 upon 5. So this is the case for specific heat of diatomic gas, correct? Now the next point is specific heat of diatomic gas at high temperature. The next point is specific heat of diatomic gas at high temperature. We know that at high temperature, which is approximately equal to 5000 Kelvin or above, the degree of freedoms for a diatomic gas will be 7. 2 additional degree of freedom because of vibrational motion. Now we have to find the value of internal energy of diatomic gas of 1 mole of substance. 1 mole of substance. If you want to find this, U can be written as 1 by 2 kBT multiplied by degree of freedoms and multiplied by Avogadro number. Now it can be written as 7 by 2 kB multiplied by Na multiplied by T. So that implies the value of U comes out 7 by 2 RT, correct? And now we have to find the value of Cv. Cv is first order derivative of internal energy with respect to temperature. So d by dt of U, and U comes out how much? 7 by 2 RT, and it can be written as 7 by 2 R d by dt of T. So that comes out Cv is equal to 7 by 2 R. We know that by Mayer's formula, Cp minus Cv is equal to R. So Cp can be written as Cv plus R. So it comes out 7 by 2R plus 2R by 2. And here we can write Cv is equal to 9R by 2. Now we have to find the value of gamma. Gamma is Cp upon Cv, correct? So this is the value of specific heat ratio gamma, and its value comes out Cp upon Cv, and it is 9R by 2 divided by 7R by 2, and it can be solved like this: 9R by 2 multiplied by 2 upon 7R. 2 will cancel by this, R will cancel by this, and the value of gamma can be written as 9 upon 7. So that's all about the value of specific heat of diatomic gas at high temperature. The remaining part is specific heat of, just a second, third part is specific heat of triatomic gas, correct? As we know that in triatomic gases there are two type of cases. One is linear and second is non-linear, correct? So when we are taking case of linear, so situation will be like this: these are the three atoms, and the formula for degree of freedom can be written as F is equal to 3n minus k. So the number of atoms are 3, so 3 into 3 minus the individual independent relations are 2, so 3 3 are 9 minus 2, so that implies F is equal to 7. So degree of freedom are 7 in case of linear triatomic gas. And now next thing is non-linear triatomic gas, correct? So situation will be like this: first, second, third, and these are the three atoms and having three independent relations. So degree of freedom F can be calculated with this formula 3n minus k. So 3 into 3 minus 3, so final answer comes out 3 3 are 9 minus 3, so degree of freedom comes out 6. Okay, so in the case of linear triatomic gases the degree of freedoms are 7, and in non-linear triatomic gases the degree of freedoms are 6. So 6 किसके लिए हैं? For non-linear, and 7 किसके लिए हैं? For linear. Please keep it in your mind. Now we have to find the value of, we are just dividing the screen into parts, U. What is U? This is internal energy of triatomic gas, and the amount of substance is 1 mole. 1 mole of triatomic gas की कितनी internal energy है, that thing we are going to find. So we will take help of law of equipartition of energy, which gives us the value of U, and U can be written as 1 by 2 kBT. So this is the amount of energy which will be carried by each degree of freedom. As we can see here, in linear triatomic gas degree of freedoms are 7, and number of Avogadro number of molecules in 1 mole of triatomic gas. Similarly for right side, I am using here red color. I can write it like this: U is equal to 1 by 2 kBT multiplied by 6 multiplied by Na. So here the value of U comes out 2 3 just 6, so it comes out 3 kb Na multiplied by T. U is equal to 3 RT, because kb multiplied by Na is equal to R, which is universal gas constant, and after that we have to find the value of Cv. Cv is equal to du upon dt, and we can write it like this: d by dt of U, and how much is U? 3 RT. So out of this 3 R is constant, and the remaining part d by dt of T. So that comes out CV is equal to 3R. Now by Mayer's formula we know that by Mayer's formula Cp minus Cv is equal to R. So that's why we can write Cp is equal to Cv plus R. Correct? So we can write Cp is equal to 3R plus R. So the value comes out 4R, and specific heat ratio gamma, which can be written as Cp upon Cv, can be written as 4R upon 3R, and it can be written as R will get cancelled, 4 by 3. So this is the value of gamma for non-linear triatomic gas, and now we are going to solve it for linear triatomic gas. So here we can write U is equal to 1 by 2, 7. So it comes out 7 by 2 Kb multiplied by Na multiplied by T. It can be written as U is equal to 7 by 2 Kb multiplied by Na. This value can be replaced by R. So 7 by 2 RT. Now we have to find the value of Cv du upon dt. First order derivative of internal energy with respect to time. So d by dt of U, it is how much? 7 by 2 RT, and it can be written as 7 by 2 R and d by dt of T. Correct? So that's why we can write Cv is equal to 7 by 2 R. We know that by Mayer's formula comes out Cp minus Cv is equal to R. So Cp can be written as Cv plus R. The value of Cv is 7 by 2R plus R can be written as 2R by 2. Correct? So the value of Cp is 9R by 2. So for that, if we are going to find the value of gamma, it can be written as Cp upon Cv, and the value of Cp is 9R by 2 divided by 7R by 2, and 9R by 2 multiplied by 2 by 7R. 2 cancel, RR cancel. The value of gamma comes out 9 upon 7. After this, the next part which is remaining, that is the value of specific heat for polyatomic gases. Now the last part, specific heat heats Cp and Cv. These two are specific heats of a polyatomic gas. So if we are just considering 1 mole of polyatomic gas, so here we have to find the value of degree of freedom of polyatomic gas. Let us consider its value is F. Means पॉलीएटॉमिक गैस जो है उसका डिग्री ऑफ फ्रीडम हमारे पास कितना है? F. एंड वन मोर थिंग, द अमाउंट ऑफ सब्सटेंस एज यूजुअल, द अमाउंट ऑफ substance will be 1 mole, correct? And the number of molecules in 1 mole, one more thing, number of molecules in 1 mole of substance, 1 mole of substance will be Na. Na means Avogadro number, correct? So here we have to find the value of internal energy as usual. So we will find it with the help of law of equipartition of energy, which says that each degree of freedom carries equal energy and that energy is equal to 1 by 2 kBT. So here we don't have any numeric value of degree of freedom, we are taking it F, and the total amount of internal energy. So what is this? This is internal energy of 1 mole of polyatomic gas. So 1 by 2 kBT multiplied by F multiplied by Na. So it can be represented like this: U is equal to 1 by 2 kb NAT. So here it can be written as 1 by 2 RT. Now if we want to find the value of CV, as usual, the formula for CV is equal to du upon dt. It can be written as d by dt of U. U is how much? 1 by 2 RT. So take 1 by 2 R common, d by dt of T, and its value comes out CV is equal to 1 by 2 R. We know that by Mayer's formula, Cp minus Cv is equal to R. So the value of Cp comes out Cv plus R. Cv is how much? R by 2, and it can be written as 2R by 2. So it can be written as 3R by 2. So this is the value of Cp, and the value of Cv is R by 2. Now if we want to find the value of specific heat ratio gamma, so that comes out Cp upon Cv, and Cp is here. Oh my god, one more thing is here the value of F. The value of F, I forgot to write here. F comes out, so F will also comes out. F will be taken out, so it comes out multiplied by F, and it comes out Cv is equal to F by 2R. Correct? In the similar way, so F by 2R, so here we can write F by 2R. So Cp, it can be written like this. Just a second. This value can be written like this. Just a second. R can be taken common. F plus 2 divided by 2. So this is the value of Cp. F plus 2 multiplied by R divided by 2. So gamma can be written as F plus 2 multiplied by R divided by 2 and divided by Cv. Cv is how much? The value of Cv is Fr by 2. So it can be written as Fr by 2. So that can gives us the value of gamma. F plus 2 multiplied by R divided by 2 multiplied by 2 F upon R. So 2 cancel, R cancel. It gives us value of gamma F plus 2 divided by F, and gamma can be written as 1 plus 2 upon F. So this is the value here, value of specific heat ratio. So that's all for this class. Thank you very much.